My name is Chance Pender and I'm a student at the University of Illinois at Springfield. I'm currently enrolled in the Chem 267 class and my professor is Dov Szabo. So today I will be looking at ibuprofen through IR mass spectroscopy. Ibuprofen is also known by the IUPAC name of 2-p-isobutylphenyl propionic acid. I will begin with degrees of unsaturation, also known as the hydrogen deficiency index, or HDI for short. So to obtain the HDI, you can use the generic equation 2 times the number of carbons plus 2 minus the number of hydrogens, all divided by 2. So the HDI tells you if you have rings or pi bonds are present in your structure. So to determine the HDI for ibuprofen, we're going to do the following work. So we have 13 carbons present in ibuprofen, so 2 times 13 plus 2 minus 18, which is the number of hydrogens present in ibuprofen, and all divided by 2. So if you do this math, you end up with an HDI of 5. An HDMI of 1 would indicate a double bond. An HDMI of 2 would represent 2 pi bonds, so this could mean either 2 double bonds or a single triple bond. An HDMI of 4 would represent a benzene ring. And so since this HDMI is 5, I'm going to assume that I have a benzene ring as well as a pi bond present in ibuprofen. So next we're going to look at IR. So IR helps us distinguish what functional groups are present in a molecule. So here you see the IR spectrum of the molecule ibuprofen. And to help analyze this, I will be using an infographic from compoundchem.com. So to begin, we're going to distinguish our fingerprint region from our diagnostic region. So where I have the blue line drawn, to the right of it is the fingerprint region, and to the left of it is the diagnostic region. For the purposes of this video, I will not be analyzing the fingerprint region because the fingerprint region does not help us distinguish functional groups and has peaks representative and unique to each molecule. So for the diagnostic region, the first region I have marked here is the carbon-to-carbon double bond. So if I had a peak here in this region, that would mean that I would have a carbon-to-carbon double bond present in my molecule. The next region over is the carbon-to-oxygen double bond. And if there is a peak here, this is representative of a carbonyl, acid, anhydride, acyl chloride, ester, amide, aldehyde, or ketone. And since there is a peak here in this region, I will assume that there is a carbon-to-oxygen double bond present in my molecule. The next region over is the carbon-to-carbon triple bond region. And here there is no peak, so I will assume that there are no triple bonds present in my molecule. And the next region over is the carboxylic acid region. And the reason why this peak is so wide is due to the presence of an alcohol that is capable of hydrogen bonding. So since we know that ibuprofen has a carboxylic acid present in the molecule, this peak here is representative of that. So the next area that we're going to look at is mass spectroscopy. So for purposes of time, I will not be discussing fragmentation. So to help analyze this mass spectroscopy of this molecule, I will be using an infographic from Compound Chem. So to begin, we're going to look for peaks that help us identify which halogens or other nonmetals are present in our molecule besides carbon and hydrogen. So here, at 43, we can see a carbon-to-oxygen double bond. And here on the mass spec graph, we can see a peak that resembles that. At 57, we can likewise see a peak that is representative of a carbon-to-oxygen double bond. And at 77, we can see the presence of another peak that also represents the presence of a benzene ring. And since there are no other nonmetals or halogens present in ibuprofen besides oxygen, we can finish here for our analysis of mass spectroscopy for ibuprofen. So we know from our IR and mass spec analysis of ibuprofen that we have the functional group carboxylic acid as well as the presence of a benzene ring in our structure. So next we have to determine the molecular formula of ibuprofen. And to do that, we're going to start with the molar mass of 206 and then subtract the largest atoms we have present in our molecule. So since we have 2 oxygens present, we're going to subtract the combination of that molar mass, which is 32. So 206 minus 32 is 174. And since we have no other halogens or nonmetals present in our molecule, we're going to subtract carbons next. So the biggest number of carbons that we can subtract from this is 14. So 14 times 12 is 166. 174 minus 166 is 8. But if we think about this, having 8 hydrogens for our 14 carbons and our carboxylic acid, that doesn't make sense. We would have a lot of vacant spots open on carbons, and that would make those very unhappy. So instead, we're gonna do 13 carbons and see how that leaves us. So 13 carbons, so that would be a mass of 154, subtract that and we get 18. Minus 18 hydrogens and we get 0. So if we think about this, this is a more acceptable answer since we have hydrogens to fill the orbitals and spots around carbon as well as for the carboxylic acid. So in the end we get the molecular formula of C13H18 and O2. Here we have some other characteristics and traits of ibuprofen, and these were taken from the MSDSG for ibuprofen. And finally, here's the bibliography for the materials that I used to create this video.